Sorry, I did not bring my the microphone today, so you'll have to just listen closely. Today we'll continue on our discussion of bootstrap and statistical inference using the computer. So I guess computational inference, and so we'll talk about non-parametric bootstrap here. Okay, and so the big picture behind non-parametric bootstrap is that you have a sample. Okay, well, and I guess this is the big picture of just statistics in general, is that you have a sample, and based on what you see in the sample, you want to know what can we say about the population. Okay, and so at that point, when you only have a sample, the best estimate of any population parameter will be the corresponding estimate from your sample. So if you're trying to estimate the population mean and you have a sample, your best estimate will be the sample mean. Okay? But you have no idea if that sample mean is even close to the population mean, or if it's too high or if it's too low. You don't have any of that information. But there are a few things you can try to get at from just looking at the sample itself. Okay, and with non-parametric bootstrap, we are not putting any assumptions on the population. So whenever you did confidence intervals and t-tests in your interest statistics class, that was under the assumption that the sampling distribution of the mean was normally distributed. Okay, so and that's coming from the central limit theorem. So we're putting some kind of assumptions and things like that onto our sample. And if you are willing to make assumptions about the population, then you can do the parametric bootstrap methods that we covered last week, where you can generate data from a known distribution and kind of compare things that way. Okay, so in our example, we're going to load this library called Bootstrap. We're only there's functions built in, but I'm going to kind of just show you how to do this Bootstrap the manual way, and we're only loading this library to get the data from it. Okay, and so in library Bootstrap, there's a data set called Law82. Okay, and what this is it's let's see. What it is it's a data set from 82 different law schools or something, and we're looking at the LSAT, I think, of the average LSAT score of admitted students and the average SAT of those students. Okay, and so this forms our population. We have 82 schools in our population. All right, so that's, I guess, as far as things go, it's a little bit smaller on the population side. And what we're going to do is we're going to draw a random sample of 15 of those law schools. Okay, and so basically I'm going to run this command: sample basically from 1 through 82, pick 15 of these. Okay, and so here this would say, we're going to pick law school number 6, law school 14, law school 78, so on and so forth. Okay, and so what we're going to do is I'm going to run just in case you want to get the same results as I do. I'm setting the seed, and then I'm going to basically subset Law 82 based on the sample of 15. Okay, and then I'm just selecting the second and third columns, so I'm just getting the LSAT and GPA score. So if I look at Law 15, I've got LSAT and GPA of my 15 selected schools. Apparently school 51, school 18, 74, and so on. Okay. Some of you guys are following along. Are you guys getting the same? What is it? 110. set.seed 110. So anyway, what we want to make inference about the correlation between LSAT score and GPA in our population. Okay. So I type in correlation, and the correlation between LSAT and GPA is around 76%. If we wish, we can plot this and just kind of get an idea of what this looks like. Okay, so these would be law schools that are more competitive to get in and requiring higher both LSAT and GPA and whatnot. Some of you might be considering law school. I don't know. Okay, and so anyway, we have our sample of 15, and we can look at the correlation between our the LSAT and GPA of the 15 schools that we selected. Okay, and here we get a correlation of 0.72. Okay, and if we want, we can plot the 15 schools that we did, okay, that we selected. And so these were the 15 schools that I randomly selected, okay, and they are just a subset. Maybe I should maybe I'll put the 2 on the same with the same limits. So x lim equal to c, we'll say 450 to 720, and y lim equals, we'll say 2.5 to 3.6. Okay, so there's that one, and then maybe we can see the 15 that we've selected. Okay, so here's all 82 schools, and these are just the 15 that I've selected. Okay, so based on these 15, we're going to try to estimate the correlation between LSAT and GPA. Okay, so again, in real life, you don't know what the population looks like. You have no idea that the 82 schools look like this. Okay, all you have are these 15, and you have no idea, are these 15 any good? And as far as you know, they could just be they could be something, because it's random sampling, you have no idea. Okay, so I'll throw these in here. Okay, so what we're going to do is we're going to just take these 15 schools that are selected, and we're going to do bootstrap. And what bootstrap is we are going to randomly sample 15 points with replacement from these 15 points. Okay, so it sounds silly, but basically we're just going to I'm going to randomly select 15 points from here with replacement. Okay, so I have my sample size is 15, and I'm taking samples of size 15, but with replacement. So chances are I'm going to get kind of duplicate. Well, there's a very high chance that I get a duplicate entry here. And based on that, we're going to further estimate things. Okay, so essentially what I'm going to do is I'm going to randomly select, so I'll do one loop inside here. Okay, so if I look at this, I'm just selecting from 1 through 15, 15 points with replacement. Okay, so here I get 4, 4, 10, 15, 14, 9, 3, 1, okay? and we're going to use these. So I'm getting even a further subset here, okay? So if I wanted to plot this, I could. Okay. Okay, and so I'm even getting a smaller portion, but some of these are duplicated in here, okay? And I could just, and every time I do this, I'm just getting another sample, and then I'm going to use these to just generate another correlation value, okay? So every time I'm just subsetting the original sample of 15, which is this. So I've got 15 data points. I'm picking 15 from here with replacement, and every time I do that, I'm going to get a correlation estimate. Okay, I'm going to do this 200 times, and we're going to just take a look at all the 200 correlations that I get. Okay, and so if I can take a look at all the different correlations I get, and you know, we get a good amount of variation here. So I can create a histogram and I get something that looks like this. Okay, so the correlation between so if we go back, the correlation between the LSAT and GPA for our 15 data points is 0.72. Okay, and so when I continually do random samples from here, we see that they're centered around 0.72. Okay, if I ask for the mean of R, we get something very close to the value in our sample. Okay, but that makes sense. Okay, and again, the bootstrap in of itself cannot tell us whether our sample is high or low compared to the population, because we have no idea what the population looks like. However, we can get an idea of the standard error of this estimate. So the correlation in the sample that we observe is 0.72. This is currently our best guess for the correlation that exists in the population. But you know, what is the standard error of this estimate? Okay, well, after running many bootstrap samples, we can just take the standard deviation of all of those things, and this gives us a standard error here. Okay, and so our standard error at this point is 0.126. Okay, so it just kind of gives us a ballpark figure as far in terms of how much error we have in our point estimate. Okay. Yes.
How is this different from if you just take every time you take 15 you get points from the original population?
Well, so we don't have the population available to us. Okay. So just for illustrative purposes, I have the population of 82 schools. Okay. But we have to pretend like that is not available to us, and all we have are these 15 data points. Okay. So we don't have all 80. We don't have all 82 available to us. If we did, then you know we don't have any question about what the correlation exists in the population and things like that. Okay. All we have are these 15, and based on these 15, what can we say about the population? This is what we want to know. Okay. And so this is bootstrap. It's without taking any outside information. We're just have the data that we have, and we're going to just do the best we can. Okay, but what we'll see is that our estimates, and a lot of this, depend heavily on the 15 data points that we do have. Okay, and so if our 15 data points that we do have are very different, then you know, it might not give a great picture. Okay, and there's no way for us to know. Okay, that's just the reality of bootstrap. Okay, but it is, you know, better than nothing in that without bootstrap you would really have no idea how much error there is, and at least with bootstrap you get somewhat of an idea, although that idea can vary wildly from one sample to another, depending on what you have. So here's just another demonstration. If I set my seed to 120, I'm just going to take another sample of 15 from the original population of 82. Okay, so again, the correlation that exists in the population is around 0.76. This new sample of 15 is much higher at 0.913. Okay, and we can kind of, this is all of the data points that we have. My random sample of 15 happen to be these 15 data points, so it's going to look like they're highly correlated. Okay, you know, and so if I run all of this, okay, so the standard error here is 0.77, and my histogram looks like this. Okay, so let's just compare. So from the second one, where our sample was very highly correlated, we got a standard error of about 0.077, and in the other example, our standard error was much higher at 0.1126. Okay, and if I just change this to, you know, something else, 125, whatever. Okay, just picking a different seed. Okay, we get something that looks very different. So again, all 82, and just a random sample of 15 there. Okay, so with random sampling, you have no idea what you've got. You just have a sample, and based on the sample, we're trying to make inference about the population, and we're not putting any assumptions on the population. Yes?
So in the loop, you're just, the correlation that you're computing is all within the sample, right?
Yeah, it's all within the sample, yes.
Okay, so the random 15 rows could repeat, like, it could be of the same row, right?
Yes, yes, yeah. So in Bootstrap, it's very important that you do replace equals true. Otherwise, all you have is just, you have the exact same sample, right? You just change the order of the points, which does nothing in terms of the correlation. So when you do Bootstrap, you have to do replace equals true, and you very probably will select the same row more than once. Okay, and with that, you are generating, you're calculating a new correlation or a new sample statistic, and using the variation from one sample to another to get an idea of the standard error. Okay? Is that okay? Yes?
I just wanted to clarify, like, I don't understand why is it legitimate for us to repeat a certain row? Is it our way of trying to see the whole population because we assume that it could be some of the elements that we find in the sample could be repeated? Or
Yeah. How is this legit? That's a good question. Yeah, I think when this method was first proposed, people were just kind of like, what are you doing? This is ridiculous. You know, you can't be pulling additional information. But it turns out, and I don't remember what publications there are, but it turns out that it's an okay method. It's legit, and it's just kind of this. There's this idea of what's called the plug-in principle, which is just, if you don't have something available, just do the best with the information you have. And that's essentially what we're doing here with Bootstrap. We don't have, you know, we only have 15 data sets or data points in our sample. We have no other data from the population. So we can't make up new data and stuff like that. So we're just going to try, well, let's just pretend picking our data points over and over again, and just kind of see how the randomness applies to the sample that we have. Okay, and we just keep taking this, and we keep going, and we can get even more what you might not expect. Okay, So we have this a bias, this idea of bias, and I wrote bias can be thought of as the difference between the true parameter value and the expected value of your sample statistics. Okay, so if you're trying to estimate the correlation in a population and you get something called a negative bias, then that means your sample statistic will tend to underestimate the true value in the population. Okay, so so things like the mean are unbiased estimators of the population mean. Okay, so if the population mean is 100, whenever you take a random sample, your sample means might be larger or smaller, but in the long run, if you do this over and over again, the mean of all of your sample means will equal the population mean. So the mean is an unbiased estimator. But not everything is like that. And so anyway, with when we're looking at correlation here, we can kind of try to get an idea of whether with our sample of 15, whether we are overestimating or underestimating the population. And this, it's not always. It just gives us an idea. And anything with Bootstrap, you've got to kind of just take your results with just like with the idea that you are making all of these inferences just from a sample without making any assumptions on the population. Okay, so essentially, when you're trying to estimate bias with Bootstrap, you have to do a whole bunch of replicates. So maybe something like 2,000. And we do the exact same thing. Okay, so this is pretty much exactly the same thing as I did before, except instead of calling it R, I'm calling it theta, theta hat and theta B. And so so the idea with bias is our current estimate of the correlation in the population is the correlation in our sample of 15. So this is theta hat. So I'll just write best estimate of population correlation with the sample we have. Okay. And theta B, this is theta bootstrap. Okay. These will be correlation estimates created via Bootstrap. Okay, and the question is, how much does or how much do our Bootstrap estimates differ from the estimate from our sample? So we're just trying to get an idea of kind of the bias that might be produced just from Bootstrap in of itself. Okay. All right, so I'm going to run this, and I'm going to run this 2,000 times. Okay. And it's very quick with the computer. Okay. And so essentially, I'm just going to take the difference between each of our Bootstrap estimates of correlation and the correlation that exists in our sample of 15 points. Okay. And so here we're getting a bias, and not a very big one. It's pretty close to 0. Okay. Negative 0.017. But it's slightly negative, so this just says our theta hat will probably underestimate the population bias. All right, I mean population correlation, population parameter. Okay, let me just I don't know if you guys want to look at that and write that down. Are there questions on what's happening? It feels very weird. Okay? Yes?
So does our sample underestimate or overestimate in this case?
So in our case, we're getting a negative bias, which means our sample statistic tends to underestimate the parameter in the population. Yes?
We like taking the standard error of like the bias, say like whether this bias is actually true, like the bias of the bias, or like.
Yeah, so we can, you can kind of further apply like, well, what would happen if I did something else? And you know, we have this luxury because we have access to the population, but otherwise, if you just have the sample, you just kind of get these numbers, and it just gives you an idea. Now, I would say it's a little it's hard to make super strong conclusions from your bootstrap estimates. Okay, I mean they're there, and you do the best that you can. But you know, if I just took the other sample, okay, so this is the, so based on this one, we got a bias of negative 0.017. If I take this one, where my correlation is much higher, okay, and we do the same exact operation here, okay, I also get a slightly negative bias here, okay? So the bias ends up being negative in both cases, even though the correlation, the sample correlation that exists in this sample is much higher than the population correlation. So the population correlation was around 0.76, and this sample happened to have a correlation of around 0.9. Even here, the bias from our bootstrap ends up being negative, okay? And over here, it was lower, and the bias ends up being estimated as negative, okay? So what does this all mean? This means, you know, if you're not willing to put assumptions on the population, the kind of inference you're limited to do is going to be kind of this bootstrap method where you're resampling the sample that you do have. And that said, it can give you an idea of kind of the standard error, and it can also give you an idea of the bias. But because you have no other outside information, you have no idea whether the sample you have is representative or if it's you know, too high or too low. Okay, it's just like so if you have confidence intervals, right? When you create confidence intervals, you have no idea if your confidence interval captures the population parameter. You have no idea if your confidence interval is too high or too, you know, if your point estimate's on the high side or on the low side or whatever. You're just kind of creating this range, and you're hoping for the best based on the what you understand of probability. And with Bootstrap, it's similar. You just have one sample. You have no idea if it's high or low versus the population. You have no idea if it gets you close to the population value or not, but you're just kind of hoping for the best based on these principles that exist behind the Bootstrap. Okay, so so that's there. Okay, are there questions?
So we're calling it bias. Are you assuming that the mean we got from the spreading is representing the population?
No. This is so. Yeah, we are not saying that this theta hat is anything close to the true parameter of our population. Okay, all we are doing, this bias is kind of a measure of the bias that exists from this bootstrap method, which gives us an idea of the bias that could happen from taking a random sample from the population. Okay, so all we're doing is to get an idea of the bias between our sample and the population. We are just going to try to use the bootstrap method to get an idea of the bias that exists just from sampling within our own sample. Okay, so it's very weird. I'll admit. Okay, it feels very strange. It's just like how is this even allowed? But it is. Okay. All right. There's another method called Jackknife. All right. I don't know where they're coming up with these terms. Apparently, the story behind Jackknife is someone thought it was like this rough and rugged method or something. I don't know. It's another idea of resampling. Okay. Except in Bootstrap, the resampling is random. Okay. You're resampling the sample that you have, and it's done random sampling with replacement. That's Bootstrap. Okay. With Jackknife, you are also resampling the sample that you have, but what you're doing is you're creating a bunch of other samples where you are just removing one point from your sample. Okay, so basically, if so, I'm going to just show what this looks like here. If your sample is the points 1 through 5, okay, 1, 2, 3, 4, 5, essentially what you're doing is you're going to just generate 5 different samples. In the first sample, you're removing the first point. In the second sample, you're removing number 2. In the third sample, you're removing number 3. In the fourth sample, you're removing number 4. And in the last sample, you're removing number 5. Okay? So it's a methodical way of resampling your sample. You are removing one point, one by one, and you're doing this for every single point in your sample. Okay? And based on the remaining sample, the remaining 4 points or the remaining n-1 points, you're going to do, you're going to calculate the standard error or the bias or things like that. Okay? And so with Bootstrap, you'd have to do like, 200 or 2,000 things. Here you're going to resample it. You're going to create n new samples, and n is the number of points you have in your sample. So if you have 50 data points, you're going to create 50 new samples, one corresponding to removing 1 point from the data set. Okay. The only thing that gets weird, and I just kind of scrambled to put our presentation together. I'll write the formulas for calculating the bias and the standard error based on the Jackknife method. Okay, because the formulas for those are a little strange. Okay, so here I'm going to just take my 15 data points. Okay, and from the LSAT or law school thing. Oops. No. All right. So this is the correlation from my sample of 15 points, and essentially what I'm doing is I'm going to just say from 1 through n, because I've got 15 data points. So 1 through 15, calculate the correlation of, and basically I'm just subsetting my data, removing row I. Okay, so the first time it removes the first row, and then the next time it removes the second row. Oh, I have to initialize that first. Okay, and so if I look at theta.jack for theta jackknife, I've got 15 15 correlation values here, okay? And this is, what happens if I remove this one? What happens if I remove this one? What happens if I remove this one? And we're just calculating correlation for every single one of those. All right. And we can get bias. It's this this funny funny calculation here. Okay, and so I get a bias of negative 0.03. Okay, also negative compared to our and I can get an estimate of the standard error. Okay, and so the standard error here is a little bit bigger at 0.167, and this is based on the Jackknife method. Okay, so is one better than the other, Bootstrap versus Jackknife? And the answer is no. There's you can't really just say one is better or worse than the other. You can also combine the two methods, and they call this Jackknife after Bootstrap. And I know, it's just like what?
So straightforward.
I know it's I know, and I didn't finish writing the code for this, but the idea here is that you create a bunch of Bootstrap samples, okay, keeping track of your data points that exist in your Bootstrap samples. So I guess I'll cover this a little bit more in detail on Wednesday, but you're gonna create Bootstrap samples, and then based on all of these Bootstrap samples, you say I'm going to remove the first data point, which then forces I'll explain this on Wednesday. It's too much. Yeah, you remove a data point, and then it forces you to throw away some of your Bootstrap samples. You don't actually throw them away, but you take them out, and then you calculate kind of the variance that exists if you remove this one data point and the corresponding Bootstrap samples that go with it. And then you do it for each of the data points. Kind of, let's say you did 2,000 Bootstrap samples, and you remove the first one, and you have to throw away like 600 of these. You kind of get an estimate. So, well, anyway, it just gives you kind of another figure in terms of the standard error and the bias and all of that stuff that exists. So I have to clean up the my R Markdown file, add a bit more commentary here, but that's what we covered today. Bootstrap and Jackknife. I'm going to post up a homework assignment also, going over parametric and non-parametric Bootstrap methods for kind of computational inference here. Okay, so we'll end just a few minutes early today. Oh, question.
When is the homework due?
Yeah, I have to decide whether I should make it due before your Thanksgiving break or after the Thanksgiving break. Well, do you guys have a preference? You guys always want, students always say like more time better, but you don't want this looming over your head over Thanksgiving weekend either, right? Huh? Make it the Wednesday before? Okay, we'll do that. I'm also considering canceling class on Wednesday before Thanksgiving. That's good? Okay, all right. So no one's going to complain that they're not getting their classes worth of money here? No? Okay. All right, so we'll do that. I'll make it due the Wednesday before Thanksgiving, and then I'll cancel Wednesday's class as well. Okay, so we'll do that, and we'll see you guys on Wednesday.